Anyone, have you gone through the content? Aryan, Bhavya, Taniska, Pratibha, Arpit. None of you have gone through the content, or in like whoever is there in the call. Can you hear me? Okay, lecture last lecture not yet completed. Okay, no problem. So I have shared this file in the GSpace also. I hope you would have gone through that. If not, I'm just going through that. So okay, so let's start it off. Just give me a second. So what I was saying, I have already shared these notes with you guys in the G space. I'll just go through it. So we started with the Laplace transform and how generally you define the Laplace transform. We started with like what was the limitation in the Fourier transform, for which type of equations or the which type of signals you were not able to find the Fourier transform. Sorry. So for those cases, we tried multiplying that signal which were non-bounded with a exponentially decaying function, right? And then we came across that if you'll multiply unbounded signal with a decaying function, that signal, that multiplied signal was becoming like integrable, okay, or becoming stable or unbounded, okay, because any signal that you, any unbounded signal, if you're multiplying with a exponentially decaying function, right? So basically that we were able to get some unbounded signal and then those were integrable, right? So basically this is what happened in the Laplace domain. So here in the Laplace transform that you calculate, where S generally is equals to your sigma plus j omega, right? And this is what we were saying, if you have a signal xt, right, and then if you are multiplying sigma times t, where sigma is greater than 0, any unbounded signal also will be become a integrable signal or an unbounded signal, okay. So this is what happens. So Laplace generally help us to calculate the, like, to move from the time domain to a S domain, right? Where S is generally equals to, S is a complex plane itself. So there you have a sigma and a omega itself. When you were dealing with the Fourier transform, where the sigma basically was zero, right? So if you have a S plane, right? S plane has what? Sigma in the x-axis and j omega in the y-axis. Whenever you have a sigma equals to zero, that means what? This totally the y-axis, right? That where the sigma generally is equals to zero, right? So that generally represents your Fourier transform itself, right? So whenever you are calculating any transform, right, when you are putting sigma equals to zero, then for any signal that you are calculating, you want to go in the S domain, like the frequency domain. If the sigma is equals to zero, that means what? The Laplace and the Fourier transform basically will be same. Fourier transform also was what? The same equation. You were having what? Xt e to the power minus j omega t, right? Dt. This is what you calculate the Fourier transform, minus infinite to infinite. Here, S was equals to what? Sigma plus j omega, right? If the sigma is equals to zero, then you both the Laplace transform and the Fourier transform become same, right? So I hope this is making sense. Why are we moving from Fourier transform to a Laplace transform? Okay, this is what I explained. We S is generally equals to sigma plus j omega, right? And this is what this generally help us to make any unbounded also signal a bounded signal. Okay, this exponentially decaying function generally helps you, right? That will decide whether the signal is decaying or not. And if sigma is greater than zero, right, there will be a decaying function. You already know that exponentially e to the power minus at, where a is greater than zero, that's a basically a decaying function, right? That will help you to make the whole system signal itself as a decaying or a stable or a bounded integrable function, right? Let's, for example, you have a signal e to the power 2t ut, right? So and then you have to calculate the Laplace transform for this. For this signal, e to the power 2t, when you were not able to calculate the Fourier transform, right? Now we try to calculate the Laplace transform out of this. What we have done is e to the power 2t, e to the power, and then the formula is pretty simple: minus infinite to infinite xt, whatever has been given to you, the signal e to the power minus st, and then you integrate it from minus infinite to infinite. We'll come to know that there are generally bilateral and unilateral Laplace transform also, but mostly you'll just deal with the bilateral, like both sides from minus infinite to infinite. Okay, you will integrate it. Then e to the power 2 to e to the power, and then we have multiplied with e to the power minus st, and then we have to integrate it from 0 to infinite, because you already know that ut is defined from 0 to infinite. So minus infinite to 0, everything will get cancelled, so you'll just be left with from 0 to infinite, right? So and this is the case that you will be getting in the end, right? E to the power minus s minus 2 t dt. Okay, now we will have to decide whether the s value is greater than 0 or not. See, s minus 2, s greater than s minus 2 greater than 0, that means simply s is a complex number, right? You can't compare the j omega part to the real part, right? So basically sigma minus 2, so real, so this was what, s minus 2 greater than 0. If this is happening, s is greater than 2, that means what, this signal, whenever this signal will be what, a decaying signal, right? If it is greater than 0, then you'll come to know that that will become an infinite value, and then you can't integrate it again, you will not be able to calculate the transform, right? So what happens, so s minus 2 greater than 0, right? So real, and we are talking about the real part. So whenever I am talking about the s minus 2 greater than 0 or anything, that means what, we are just talking about s ka real part, not the imaginary part. We can't compare imaginary part with the real value, right? So that's why whenever you have been written in any form, in the s form, you just have to worry about the real part. Okay, so here also the real part of s minus 2 should be greater than 0, and the real part of s should be greater than 2. Okay, and later you come to know that this is what the region of convergence, right? So wherever the sigma was greater than 2, okay, if sigma is greater than 2, for those reason you are able to calculate the Laplace transform. For the same function you will be able to calculate the Laplace transform, and you'll not be able to also. So it all depends on the which are the region of convergence where the signal is generally getting converged, and you are able to calculate the Laplace transform. Okay, so for this case, wherever you are not able to calculate the Fourier transform, you are able to calculate the Laplace with some region of convergence, some limitation. Okay, so the limitation is the ROC, and this is very important, the ROC, the region of convergence for the signal, for the Laplace transform at least. Okay, so wherever you have to calculate for the same signal, you can get a two different, or like for a two different signal you can get a same Laplace transform, but the region of convergence will be different. So you have to worry, and you have to check every time the ROCs also. For any function that you have to calculate the Laplace transform, you should be knowing about the region of convergence also. Okay, is that clear to everyone till now? Okay, okay. And this is what I was saying. If s minus 2 is less than, if the sigma is less than 2, for those cases you are getting some infinite value, and those cases you are not able to calculate the Laplace itself. Okay, so that is what I was saying. Now, how will you denote a Laplace, or how will you generally denote the ROCs on a S plane, or okay, the complex plane? So the case was what, the sigma should be greater than 2, right? And you will have to, it should be there in the mind, right, that ROC never contains the pole of a Laplace, like any signal that you have, the Laplace transform will be having some zeros and poles. ROCs never contain the poles of the system or the signal. Okay, so here also I represented like this, right? So for all those reasons except this two, so sigma greater than 2, right? For these cases, you are able to calculate the Laplace transform for the given signal. Okay? Yeah, the pole is 2. I'll give you some tricks also how to directly calculate the poles and the zeros. Like poles and zeros is pretty simple to calculate. It's not that difficult. Here also I've written in the notes also 2 is not included in the ROC. So ROC never include the poles of a signals. Okay. Now you have to calculate for e to the power minus 2t ut, right? The same procedure you will follow, the formula that you know, you have to just integrate it from minus infinite to infinite xt e to the power minus st dt. Okay, so the same thing you'll have to use, just put the value of xt as e to the power minus 2t. Here, see, whenever you were having e to the power 2t, right? So this generally tells you the poles. Okay, here minus 2 is there, so that generally tells you the pole of a system. Or directly you can calculate the Laplace transform and then see what is the pole that you are getting. So here, what is the value you are getting? Poles is generally where the denominator part is getting 0, right? So s minus 2 equals to 0 plus 2 equals to 0. That means what? S equals to minus 2. So minus 2 is the pole. Okay, and here also when you were integrating, you came to know that s minus s plus 2 should be greater than s plus 2 should be greater than 0. Okay, then only the system will be like this signal will be integrable. Otherwise, it will not be integrable. Okay, and then I'm talking about s plus 2 greater than 0. That means simply real part of s greater than minus 2. Okay, so here also you can see that for all those reasons, sigma greater than minus 2, the Laplace transform we were able to calculate, and Laplace transform generally exists for this region of convergence. So ROC is very important for the Laplace transform. If you are unable or not able to find the ROCs, then uh, you might do the mistake also in the exam. So I told you, right, different type of signal can also come up with the same Laplace transform, but the ROCs will be different for a different signal. Okay, I'll give you examples also where two different signal was having a same Laplace transform, but the ROC is different for both the cases. Okay, so here the ROCs becomes very important. See this thing, you can see that Fourier transform e to the power 2t ut, the Fourier transform doesn't exist, right? But Laplace transform exists, and that too with a condition that sigma should be greater than 2, sigma should be greater than pole. And this you can directly think of also. See, this signal is right-handed signal. Okay, okay, just give me a second. I guess my laptop. Are you able to hear me, everyone?
Yes, sir. Yes, sir.
Yes, sir.
Okay, just give me a second. Okay. So what I was saying, it is about 2t ut. So here the Fourier transform doesn't exist, right? Because you can see that the signal itself is not integrable, right? Because e to the power 2t exponentially like increasing function, right? You can't integrate it from 0 to infinite to infinite. Okay. So now, but for the Laplace transform, we saw that you are able to calculate the Laplace transform for those signal, and how, with some condition we are applying, right? Condition is what? That sigma value should be greater than 2. Okay, just give me a second. I'll just. Yeah. But for sigma less than 2, the Laplace transform also doesn't exist, right? Because again, the signal will be non-integrable, right? Again, similarly, and one more thing that I was telling about. So basically, if the Laplace exists, then no, it's not Pratibha. You can get Fourier transform also for many signal, and similarly the Laplace transform also. Okay, but but you can get many times. What happens, you'll not be able to get the Fourier transform for a signal, but you can get the two Laplace transforms. Okay, so it's not like for many signal, for let's for example delta signal or many other signals, you'll get both. You can calculate Fourier transform also, or you can calculate Laplace also. Okay, but for many signal you'll not be able to calculate Fourier transform, but you can calculate the Laplace transform, and you'll see that in the coming circuit and analog like EC, wherever you will be dealing with, wherever the circuit things come or transient analysis you have to do, mostly you'll just be dealing with the lab. You just convert that time domain to the S domain or the frequency domain, and mostly you'll be using the Laplace transform itself to deal with the circuit type of questions where you have to analyze transient thing and all. And then you'll come to know about the other things also, like whenever you are dealing with some system, and then if you are applying some simple exponential function or some sinusoidal function, how does the normal LTI system react and all. Okay, so there also the Laplace will help you a lot. Now, what I was trying to say is, if you have been given, so this system is what? This signal is what? Left-handed signal. Sorry, right-handed signal. Because ut is defined from 0 to infinite, so this is a right-handed signal. And you can see that the sigma, the ROC also you can just think of as the ROC will be right-hand side of the pole. So the pole is 2, right? So this signal was right-handed. So here the ROC also you are getting as right-handed, right? Here also you can see that e to the power minus 2t. So you are able to calculate the Fourier transform, right? Here also you are able to calculate the Laplace also with some condition, and the condition is what? Sigma should be in the right side of the pole. Okay, here also the system is what? Signal is what? Right-handed, and here also the ROC you are getting as right-handed, right? Sigma greater than -2, sigma greater than the pole that you are that is existing. Okay, and for less than -2, the Laplace transform doesn't exist. I hope this is making sense. So I just wrote all the tricks also. How can you remember these all things? So if you have been given a signal, right, it is about 2t. So 2 is the pole. So if it is written in this way, 2 is the pole. Or you can calculate the Laplace transform also. You'll be getting 1 upon s minus 2. S minus 2 equals to 0. That means the pole is 2. Okay. If this is a right-handed signal, right, your ROCs will also be what? Sigma greater than 2. Okay. This is pretty simple to remember. Similarly, if you have minus e to the power 2t, u of minus t, right? This is what? This is u of minus t, minus infinite to 0. So this is left-handed, right? If this is left-handed signal, okay, so you will be getting the ROCs also in left-hand side of your pole. So pole is what? 2, right? So the similar signal, right? One is for right-handed, one is for left-handed. Your ROC also, you can see that, right? This is almost similar, right? If the signal is right-handed, your ROC is also sigma greater than the right hand side of your pole. Okay, here also. So this is a very basic, like it's not that difficult to remember this all things. Okay, we'll come to the properties also. This can you can directly calculate it to the power 2t u of minus 2t. You can directly calculate it. So here one thing is like here minus sign is also there. Or if you are not putting minus here, just put minus here. Okay. So I hope this is clear to you guys. Now we'll come to the property. So, so see that all the properties that will be dealing here will be same as whatever we have done it through the Fourier transform or the Fourier series, almost similar. So here also the linearity property. Let's for example x1t has a Laplace transform of capital X1s, or x2 also has a Laplace transform of x2 with the ROCs R1 and R2. Now what will happen if you have a linear like linearly added, let's for example a times x1 plus b times x2. If you have to calculate the Laplace transform, what will you do? The constant part will get multiplied similarly as you were doing for the Fourier transform also. Okay, the only thing here is the ROCs. The ROCs you have to take care of. The ROC will be the intersection of R1 and R2. Okay, not the union, it's like intersection. Okay, the common of two. Let's for example here this exists from sigma greater than 5 and this exists from sigma greater than 4. What do you think? What will be the ROC? If one signal is existing greater than 5, one is existing greater than 4, what do you think? What will be the ROC? Greater than 4 or greater than 5?
Greater than 5.
Correct. So that will be greater than 5. Okay. Now, similarly, let's for example, we are dealing with the example. So 4 times e to the power minus 3 to ut minus 6 e to the power minus 70 ut. So you already know that for this e to the power minus 3t. So minus 3 is the pole, right? So s equals to minus 3 is the pole, right? What will be the ROC? ROC, I told you, this is a right-handed signal, sigma greater than minus 3. This will be the ROC for this first case. Similarly, for the second case, it will be sigma greater than minus 7. If you have sigma greater than minus 3 and sigma greater than minus 7, what will be the ROC? Sigma greater than minus 3, right? Is it clear to everyone? Yeah. Similarly, and you already know how to calculate the Laplace transform. For e to the power minus 3t, this will be 1 upon s plus 3, and for this case, 1 upon s plus 7. Simple. Okay. So at least for the exponential function, now you know the how to calculate the Laplace transform. Now the second property is the time shifting property. Same thing that we were doing in Fourier transform. Here, if you have xt with the Laplace transform of capital X, then if you are doing some delaying of the function or advancing the function, what will happen if your signal becomes x of t minus t naught, right? If you are shifting right hand side, what will happen? Just you multiply with e to the power minus s t naught. You can, and similarly, if you have the signal x of t plus t naught, your signal will become xt times e to the power st naught. Okay, so the sign is same. You can see that here it is minus and here also it is minus. Here it is plus, here also it is plus. Okay, it's very simple to remember. The most important thing here is there won't be, if you are doing a time shifting in the signal, there won't be any changes in the ROC. Okay, so there will not be any changes in the ROC. So there's a thing to remember. See, whenever your Laplace transform is, if you are doing anything on S, okay, on the Laplace transform, then only your ROC will get changed. Otherwise, it will not change. So here we are not doing anything on the S, so that's why there won't be any changes in the ROCs. Okay. Now the next thing is, let's for example for UT you have to calculate. How will you calculate? So simple, right? Minus infinite to infinite. But the signal will be defined from 0 to infinite. So you can just integrate it from 0 to infinite. It will power minus STDT. Okay. It will be very simple, right? What will you get? 1 upon S. So this is what, see, you have just UT. UT is, you already know this is defined from 0 to infinite. You have to integrate this function. It will power 1 times it will power minus ST dt from 0 to infinite. Okay, and when you will integrate it, you will get the value of 1 upon S, and it's pretty clear also. And here the ROC that you will be getting is S greater than 0, because from here it is power minus st, right? So S should be greater than 0 to make the signal integrable, right? And S greater than 0, that means what? Real part of S greater than 0, that means sigma should be greater than 0. Okay, so you can remember some of the very important signals ka Laplace also. Like for example, for exponential function, you can remember all those combination of the exponential function. Similarly, for the unit step function also, you can remember the Laplace transform, that is 1 upon S with a ROC of sigma greater than 0. Okay, or S greater than 0. Now, if you have been asked to calculate for u of t, if you are just delaying the signal, like if you are just putting the shifting the signal right hand side, right, what will happen? The ROC will not get changed. Only thing will happen is e to the power minus of 3 times S will get multiplied with 1 upon S, right? This will be the Laplace transform, but the ROCs will not get impacted. Okay, is this clear to everyone? Okay. Now the third property is, okay. So without even seeing that, what did I say? I said that whenever there is a change in the S, then your ROC will change. Is there any change that we are doing in the frequency shifting? If let's for example, if you are multiplying it about S naught T, is there any change in the S in the right hand side? S is getting shifted, right? Earlier it was the Laplace transform was x of s. Now the Laplace transform is what? If you are multiplying e to the power s naught t, your in the frequency domain, the s is getting shifted, right? It is shifted right side, right? It's got s minus. So you are just what you are doing. S is like s minus s naught. You are just replacing s with s minus s naught, right? So you are doing something on s. Correct? If you are doing something, that means what? The ROC will change. And ROC, how will the ROC will change? You just have to replace sigma with sigma minus whatever the value that you are getting, sigma minus S naught. Okay, is this clear to everyone? So this is very simple to remember also. Okay, see, ROC will change because I told you, right? Whenever there's an impact on S, then your ROC will change for sure. Okay, here also, let's for example, you were having UT. UT, you already know that Laplace transform is 1 upon S with sigma greater than 0. That is the ROC for UT function. Now let's for example you're multiplying e to the power 80. You already know that for e to the power 80, what is the Laplace transform? 1 upon s minus a, that we have seen earlier, right? And s greater than a, because this is the right handed signal. Your ROC will also be in the right hand side of your pole. Okay, or you do use the frequency concept. Okay, the property that we have dealt. So what we have dealt, if you are multiplying anything as e to the power s naught t, here it is what? E to the power a t, right? What will happen here? S minus a. Correct. This is what happened. And what will be the change in the ROC? ROC sigma will get replaced with sigma minus a. It's very simple, right? So here also, earlier the sigma was sigma greater than 0, because here for ut function you were having just sigma greater than 0. Now you have multiplied e to the power 80, so there will be an impact in the frequency domain, right? What is the impact? S will get replaced with s minus a. Okay, if s is getting replaced with s minus a, means what? This 1 upon s will be, s will get impacted by s minus a, so your function will become, the Laplace transform will become 1 upon s minus a. What will be the ROC? ROC, I told you, right? Sigma will get replaced with sigma minus a. So now Earlier sigma was greater than 0. Now it will be sigma minus a greater than 0. So that means what? Sigma greater than a. Correct? You do it with the basic formula or you use the property, you'll be getting the same Laplace transform, and the sigma or the ROC value also as the same. So from till now, what I've taught you three properties. One, the linearity properties, where there also the ROC was changing because we were having two functions, right? So it will be the intersection of those two ROCs function, right? The second thing that I taught you was the time shifting property. In the time shifting, you are not impacting anything on the S domain, right? So if you're not impacting anything on S, there won't be any change in the ROC. The third property was the frequency shifting. In the frequency shifting, you are changing the frequency, right? The S value. So if you are changing S value, that means what? There will be a change in the ROCs also for the signal. Okay? Is it clear to everyone? Just give me a second. Okay. So till now, I hope I discussed about the three properties, right? So now the next property is what? The time differentiation properties. Okay. Okay. So time differentiation properties. That is the fourth properties, right? So now this properties we have already dealt in one of like almost we have dealt in the Fourier series and Fourier transform also, right? So here also, let's for example for xt you know the Fourier Laplace transform. Okay. So now what will happen if you have to get the Laplace transform of differentiation of xt, right? Let's for example you have calculated for ut. Now you have to calculate for the delta t function. Delta function is what? If you have ut, if you know the Laplace transform of ut, you can just differentiate, right? Ut function, you'll get the delta function, right? If you have to calculate for the del function, you can directly calculate the Laplace transform, and that will be what? S times 1 upon s. Correct? Is this clear to everyone? Yeah. So, and this properties we have learned in the Fourier transform, right? Where you are just replacing s with j omega, right? So, if you have to get the Fourier transform of any function, differentiated function, you are just multiplying with j omega times the Fourier transform that you were getting from the like xt function. Okay. Now, and here also there is no change in ROC because you are not impacting the s, right? You are not shifting, doing anything on s value. So that means what? There won't be any changes in the ROC also. Okay, so till like four properties we have to. So after reading all the properties, we'll try to solve some of the questions also. Okay, so now I told you, right, if you have to calculate that for the del function, right? For the del function, if you have to calculate del function is what? The differentiation of your ut function, right? So if for ut function, if you know the Laplace transform, right? Similarly, you can calculate it for the del function. So del function is what? Differentiation of ut function s times 1 upon s, right? Here also sigma greater than 0. But there is one thing for the delta function, this is a special function, right? So here also the ROCs will be all. So for the ut function, sigma was greater than 0, right? So this del function is the only exception that you have. Here the ROC will be any value. So this will be for sigma belongs to all R. Okay, is this clear? Yeah. So now the next property is the frequency differentiation properties. And this also we have dealt it so many times, right? If you have a signal xt, for that you have a Laplace transform. If you have to get the Laplace transform of t times xt, right? What will happen in the Laplace transform? You have to differentiate that function with respect to s and then sign, put the negative sign. Here also you are not doing anything on s. That means what? There won't be any changes in the ROC. Okay, it's pretty simple, right? To remember everything. Till now, for which of the like which property you have changed, like the ROC was changing. One for the linearity and the other was the frequency shifting. Because in the frequency shifting, we're shifting the value of s itself. So if you're changing s, that means what? The sigma will get replaced with the similar like the value. If s is getting replaced with s plus a, then sigma will get replaced with sigma plus a. And then you use the same equality, you'll get the value of the ROC. Here, you're not doing anything else. That means what? The ROC will be same. No change in ROC. Okay, clear? Again, let's for example, for e to the power minus 80 ut, you already have the Laplace transform 1 upon S plus A. Sigma greater than minus A, right? This is a right-handed signal. You need right hand side of the ROC will be right hand side of your pole. Similarly, if let's for example, if been asked to calculate the Laplace transform of t times e to the power minus at ut, what will you do? You know the property. If you're multiplying t here, then you just have to differentiate this 1 upon s plus a with respect to s and then put the negative sign. Okay, you'll be getting the and the ROC will be same, sigma less than greater than minus a. Okay, now the next property is the scaling property. So here in the Fourier series there is no impact in the scaling. If you are doing the scaling also, there won't be any impact on the Fourier series coefficient. Fourier series only the impact will be that the Fourier series constant coefficient value will be same. Only there will be the omega will change, right? The fundamental omega will change. Here, what will happen if you are applying a scaling property? Let's for example for xt, you have the Laplace transform. If you are multiplying a here, what will happen? A mod of a will get divided. The whole function, the Laplace will get divided with the a constant, and everywhere the s will also will replace with a s upon a. Right. So now you can see that here s is getting replaced with s upon a. Correct? That means what? There is a change in s, right? That is happening, right? That means there will be change in the ROC also. Till now, many of the properties that we have dealt where the s was not getting impacted, then the ROC was same. But here s is getting impacted. S upon a. That means what? Sigma also will get replaced with sigma upon a. Simple. Okay, let's for example, e to the power 4 minus 40 ut. You have been given. You have to calculate the Laplace terms. You already know that for this signal, minus 4 is the pole. That means what? 1 upon s plus 4. And sigma greater than minus 4. Okay. And now what I have been asked to calculate the Laplace transform of e to the power minus 12t. Okay. If you have been asked to calculate for the e to the power minus 12t, what is there? You just are putting t to 3t. That means what? This will get divided with 3 and then s will also get divided with 3. Correct? See, let's for example, this was given. The signal was given something like e to the power minus 12t ut. Okay, what will the Laplace transform? 1 upon s plus 12. And what will be the value of ROC? Sigma greater than minus 12. Correct? If you will use the property, let's for example, here we are using the property, right? From properties also, what will happen? Here, 1 upon s, so 1 upon s upon 3 plus 4 and 1 upon 3. Correct? So region of convergence what will happen? 1 of s. So sigma get replaced with what? Sigma upon 3. And then sigma by 3 greater than minus 4. That means what? Sigma greater than minus 12. Correct? We are getting same value, right? If you use the property or go with the basic approach. Is this clear to everyone or not? Clear? Everyone? Okay, so the next property is the time reversal, and that is also same. Like if you are just almost in the Fourier transform, also you have dealt with that. So if you are just replacing t with minus t, you're in the Laplace transform, the s will get replaced with minus s. And here also, if you are changing, there is a change in s, right? So that means what? Sigma will get replaced with minus sigma. Pretty simple. The next property is the convolution. So these are all the properties I'm just going through. I'll just solve some problem also with the help of these properties. Okay. So this property should be, so I just, that's why I just read it in the form of a note so that it'll be better, like good for you to just go through it. Okay. And it'll not be taking much time to remember also. It's like almost you're repeating the same thing for the Fourier series, then Fourier transform, and then the Laplace transform again. Here again, the time convolution. So if let's for example, you have been given two signals, right? For both the signal, you know the Laplace transform, right? With the ROC R1, R2. Again, here what will happen if you have to get the Fourier transform, sorry, the Laplace transform for the convolution function, x1, x2 ka convolution. Okay, this is the convolution, right? Then in the Laplace domain, this will get multiplied. So you have x1 capital X2, right? You'll just multiply it. You will be getting the Laplace transform of the convolution of x1, x2. Okay, the ROC will change here, and the ROC will be what? The intersection of both these two functions. The whatever the ROC was there, R1 was the ROC for the first signal, and R2 was the ROC for the second signal. So it will be the intersection of both the signals. Okay, Now this you have to solve it. So this is pretty simple, right? This we have already, this you can solve with the linearity, right? So let's, for example, for the first case, what will be the value? 1 upon s plus 3. Similarly 1 upon 7 plus s plus 7. So for this signal, what will be the 1 upon s plus 3, 1 upon s plus 7? Here the sigma will be what? Sigma is greater than minus 3. Here the sigma is greater than minus 7. Right? The ROC. So for one signal, this is minus 3, this is minus 7 for the other signal. That means what? The ROC will be what? The intersection of these two. Intersection is what? Sigma greater than minus 3. Is this making sense to you guys? Everyone is able to understand this? Very simple, right? Now, there are some functions. Let's, for example, the cos function, cos omega t. So for this cos omega t and all, this is also very simple to like calculate it, right? How generally you get the this cos function? How do you get the Fourier transform, right? So sorry, the Laplace transform. How do you get the Laplace transform for the cos function and for the sine function itself? And these are very simple. How can you write the cos function? Can you write? How will you write the cos function in the term of exponential function? Anyone? See, a cos t. How do you write the cos omega t? E to the power j omega t plus e to the power minus j omega naught t upon 2. Correct? You already know that for this type of a signal, what is the value? For any signal, 1 upon, sorry, e to the power j omega naught t. Correct? You already know what will be the value, 1 upon a plus j omega naught. Similarly, for e to the power minus j omega naught t, what will be the Laplace transform? 1 upon, that is the Fourier transform, right? So e to the power, okay, sorry. So for e to the power j omega naught t, you will be having the Laplace transform, right? S minus j omega naught. Similarly, you got minus j omega naught t. You'll be having 1 upon s plus j omega naught t. Correct? You just add both. What will be getting? S square plus omega naught square. Correct? And the upper side you'll be getting s plus j omega naught, and then s minus j omega naught. This will get cancelled. You'll be left with what? You'll be left with 2s upon 2 times s square plus omega naught square. Right? 2 get cancelled. You'll be left with what? S upon s square plus omega naught square. Is this clear? So this is how you calculate the Laplace transform for the cos signal. Similarly, you can calculate for the sine signal also. The same process, right? E to the power j omega naught t minus e to the power minus j omega naught t by 2, right? Similar for this function, you know the Laplace transform. For this function also, you know the Laplace transform. And you use the linearity properties, you'll be able to get the Laplace transform for the sine function also. Is this clear to everyone?
Yes, sir.
Correct. Similarly, see, for the, you were calculating the Fourier transform, right? Fourier transform, you're getting this value, right? Okay. But for the Laplace transform, you're getting the value as this. So this should be there in your mind. And let's, for example, you're multiplying something into the power, you're multiplying into the power minus 80 here. So which property will be used here? If you're multiplying into the power minus 80, what will be the impact on the Laplace transform? S plus A. Here also S plus A whole square. Correct? This is what happens, right? If
Yes,
you're multiplying
yes, sir.
exponential here,
Yes, sir.
correct. So there will, right. So there will be shift in the frequency domain, right? So this is what happens. So I already told you about the unit step function also, 1 upon s, and for 1, here for 1 the Laplace transform is not possible, and you can see that also. Why? Because 1 you can write it as what? Ut plus u of minus t. Correct? For this signal it will be 1 upon s, for this signal minus 1 upon s. But the problem here is the ROC. Here the sigma greater than 0 and here sigma less than 0. There is no intersection point. Correct? So that's why for 1, okay, that's this function, the Laplace transform is not possible. See, the derivation also has been given here. For ut you have 1 upon s. For u of minus t it is 1 upon minus 1 upon s. This is a right-handed signal. Right hand side of the pole sigma greater than 0. Left hand side of the pole sigma less than 0. So there is no intersection of these two. So that's why for signal 1 the Laplace transform is not possible. Okay. So what I was talking about the bilateral and the unilateral. So bilateral is nothing, you are just integrating from minus infinite to infinite, and the unilateral you are just integrating from 0 to infinite. Nothing. Uh, Mostly you will be here. You will just be dealing with the bilateral. If you have been asked to calculate the Laplace transform, you will have to understand that this is talking about the bilateral. You just have to integrate it from minus infinite to infinite itself. Okay. Many times you use 0 to infinite whenever you deal with the circuit questions. Okay. Where because here you need 0 minus also. Okay. How the circuit was behaving, how the inductor was behaving just before we are just switching on the circuit. Okay. So that's why unilateral Laplace transform generally you use it in the whenever you solve the problems of the circuit questions. Okay. Where you just need the voltage across the capacitor, okay, the current across the inductor before you're just switching on the circuit. Okay. So that's why you just deal with the unilateral Laplace transform there. Now there is some uh, like 9 diagram I have just made. Okay. So just to make a conclusion that the poles never exist inside the ROC of a function. So let's for example you have been given some 9 combination of with the help of the exponential function itself. Okay, with the exponential function I have created 9 different combination. Okay, of the ROC that can happen. Okay, now see you can see that the first 3 signals,
Okay, sir.
yeah, all the first 3 signals are causal signal. You already know that causal signal, that for the causal signal generally defined for the right handed signal, right? This is what generally you define the causal system, right? Okay, so what I was trying to say, see, if you have been given, see from the ROCs, right, you can get an idea about the whether the system is causal, or you can get an idea about whether the system is stable or not. That also you can get. And if you are talking about this the signal, then you can tell about whether the signal is integrable, right? If you're just dealing with the signal, that means what you can say that the signal is integrable or not. You can't say that signal doesn't have like that thing of stability or unstable. System generally have, right? So if you are, let's say example, this all things that has been given as a impulse response of a signal, impulse response of a system, right? If let's say example e to the power minus 70 ut plus e to the power minus 3t ut, these are all the impulse response of a system, right? Then you have to tell about whether the system is what stable or causal or what, right? Then from the ROCs you can get an idea, right? The first thing is you can see that the first 3 diagram, right? The ROCs are what right-handed side, right? The ROC all the you can see that the right-handed, right most of all rightmost pole, whatever the rightmost pole is minus 3, here it's 3, here it is 7, right? Rightmost of the pole, so the ROC is generally the rightmost of the pole, right? And how do you define this generally the causal like the system itself, right? How do you define the causal system? The system generally define it as how when the function value is 0 if the t is less than 0, right? This is how generally you define the system, the causal system, correct? And for stability how do you define? So how many you have not like we have studied right about the systems and all, right, in one of the week 7 or 8, week 5 6, right? See here I just want to tell you from the RSC you can get an idea. The first thing that should be there in your mind is never the pole will exist inside the ROCs. Okay, that should be there in your mind. Okay, and you can see that also whenever if it is happening, that means what, that the Laplace transform is wrong, or at least that doesn't exist generally. Okay, the never the pole will can never exist inside the ROCs. Okay, you can see that also. That's why I was telling you also, you generally write it, represent it like this, so that the minus 3 will not be coming under the ROC of the function of the system that has been given to you. And one more thing that I was telling is I told you in the last session also, whenever you have been given the ROC, and if the j omega axis, the y axis for this complex plane, that is j omega, right? That comes inside the ROC. That means what? The system is stable. Okay. So there's two things that I was telling. I'm telling the last session also. I told you whenever the ROC will never contains the poles of the system, and the second thing is, if you are the ROC containing the j omega axis, that means what? The system is stable. Okay, so this is very important, and that will be asked in the exam also. Okay, regarding this. So I told you about the, here also it has been written. Okay, everything has been written for the causal system, and the first two, first, second, third are the causal, because you can see that for the causal ROC will be right hand side of the rightmost pole. Okay. Okay, so for the causal system, because you can see that the first, second, or third, so all are right-handed side signal, right? From the UT, you can get an idea, right? All are right-handed side signal. If we are dealing with a causal system, right? So the ROC that will be getting the right most pole, whatever the ROC will exist in the side of the rightmost pole of your whole system. Okay, so you can see that these three are causal system, right? So if the system is causal, the ROC will be right hand side, the rightmost, whatever the rightmost poles are there. Here -3 is there, here 3 is there, here 7 is there. So that's why the ROC is existing in the right side of that. Okay, that is the first case. If you are dealing with a causal system, see, let's for example, if you are not dealing with the causal system, that will not happen. So this is not causal, right? So this is not happening, right? So here also many of the things you can say that whenever you're not dealing with the causal system, then you can't say. But if you're dealing with the causal system, you can say that the ROC will exist in the right side of your rightmost pole. And about the stability also, I told you, right? If the ROC contains the j omega axis, then you can directly say that the signal will be absolutely integrable. But if you are dealing with the system response of the system, or you're dealing with the system, that means what? The system will be stable. Okay. Now, so I guess these all things I have already dealt with this. The only thing that I was talking about, if you are dealing with a unilateral, that generally you deal in the circuit type of a problem, right? So you would have heard like or studied in EC also. Whenever you were differentiating, right, there was some constant value also was coming, right? But here for the bilateral, what we are assuming, all the initial condition generally we assume it as a zero for the bilateral condition, right? But in unilateral, you have all the initial condition also, like x0, x0 minus and all, right? So that's why this will be the property. Generally will not deal with that in the signal system. Generally you deal with all these things whenever you deal with the circuit type of a problem. Okay, but it should be there in your mind also. There can be questions also from the unilateral also. It will be mentioned directly, right? So all these things you should be having in your memory. Okay, is this clear to everyone?
Yes, sir.
Okay. Now, similarly for the integration properties also, the integration property is pretty simple if you are dealing with the unilateral. So see what was happening if you are difference in the differentiation. What was happening in the difference when you have to calculate for a differentiated signal. If you have to calculate the Laplace transform, you are just multiplying s. In the integration, you will just divide it with s. This is what generally will happen. Okay, so let's try to solve some problems. So I'll just when is okay, or one more concept is there, initial value theorem and the final value theorem. That is also very simple. It's not that important, it's important but it's not very simple to understand it. Okay, so let's for example, this also generally will be helping you whenever you deal with the circuit type of a problem, right? So what happens, you have been asked, right, at t tends to 0 or t tends to infinite, what will be the value of some capacitor voltage or something like that, right? So there, if you are dealing in the Laplace domain, it will become very simple for you to calculate anything. Okay, so these are all, you can see that, and this initial value and the final value theorem, these are all dealt with the unilateral Laplace transform. Here, see, if you have to calculate, let's for example, you have been given the time domain. Okay, any function you have been given in the time domain, if you are able to calculate the Laplace domain for those time domain function, right? If you are going, if you are able to calculate the Laplace transform for those signals, right? If you have to calculate x0, right? So you can directly calculate in spite of t0. If the circuit, if you are not able to get the time domain, if you have the Fourier transform, the Laplace transform, what you can do is whatever the Laplace transform that has been given to you, multiply s and then put s tends to infinite, right? So this value generally gives you the value for any signal when at the initial point. So this is what generally you call it as an initial value theorem. Similarly, you have a final value theorem also, where you have to calculate the, if you have been asked to calculate in the steady state the value of anything, the voltage or the current across the inductor, right? So if you have been asked to calculate the in the steady state, right? If you have the Laplace transform for those signal like circuit, if you are able to calculate the Laplace transform, what can you do? You just put the value of s equals to 0. Okay, so this is how generally you calculate the, this is what the initial value theorem, the Laplace and the final value theorems are. Okay, the poles and the zeros, I hope you're already aware of. Any signal or system that has been given to you, you are already aware of the what are the poles and the zeros of any signal. Okay, now let's solve some of the problem. Okay, so let's try to solve at least three problems. Okay, and then I also have to leave. So I'll also try to close this session by 9 itself. So let's try to solve the first question. How will you solve? Can just somebody tell me how will you solve the first question? If you have to calculate the area under this curve, how will you calculate? See, for this signal, if you have to calculate the Laplace transform, how do you calculate the Laplace transform? Minus infinite to infinite, right? Zt to the power minus st dt. Correct? This is the Laplace transform, right, of gt. So if, let's for example, you have the Laplace transform, right? And then you put the value of s equals to 0. If you put the value of s equals to 0, right? This will get cancelled, right? This will be 1. And this will be remaining, the remaining part will be what? Minus infinite to infinite gt dt. Because you have kept it s equals to 0, right? And if, let's for example, you have the Laplace transform, here also you put the value of s equals to 0, you'll get the integrated value. This is pretty simple, right? Let's for example you calculate for sine 2 pi t, for sine omega t, what do you get? Omega upon s square plus omega square. So you have 2 pi t, so it will be 2 pi upon s square plus omega square. But now it is multiplied with e to the power minus t. You already know that if you multiplied with e to the power minus t, what will happen? S will get replaced with what? S plus 1. Correct? So now the Laplace transform will be what? 2 pi upon s plus 1 ka whole square plus 2 pi ka whole square. Is this clear? And then put the value of s equals to 0. You'll get the area under the curve. Is it clear to everyone or not? Should I explain it again? Or should I write the solution? Okay, let's write it down.
So please write the solution. Yes, sir.
Okay, I'll just write it here, the solution. So this was the solution for the first example. So you have for sine omega t ut, what is the Laplace transform? Omega upon s square plus omega square. Now here it is sine of 2 pi t ut. So you have 2 pi upon s square plus 2 pi whole square. Now you are multiplying also to the power minus t, sine of 2 pi t ut. So you have 2 pi upon s plus 1 ka whole square plus 2 pi ka whole square. Now you have been asked to calculate the area under the curve, right? So this function is gt, and then you have been asked to calculate area of gt, right? That is basically what? Minus infinite to infinite gt dt. Correct? How can you get this? So if, let's for example, you are calculating Laplace transform of gt, that is equals to what? Minus infinite to infinite gt e to the power minus st dt. If you'll put the s equals to 0, you'll be left with what? Minus infinite to infinite gt dt. Right? That is basically equals to what? Whatever the Laplace transform that you are getting, put s equals to 0. Correct? So we got the Laplace transform as this. Put s equals to 0 here. So the area that you'll be getting is what? 2 pi upon s, sorry, s was 0, right? So this is 0. So 2 pi upon 1 ka whole square plus 2 pi ka whole square. That will be the area. Correct? Are you able to understand this, everyone?
Okay, sir. Yes, sir.
Yeah. Now let's solve the second problem, and that will be the last problem. The remaining you can solve it, or maybe I'll just upload it the solution, or maybe I'll just solve it on the Saturday session. The second problem is this is also, so you have xt. Okay, let's write it here somewhere. Okay, I'll just copy this question. Okay, so what you have to do is you already know that xt. So let's, for example, I have to calculate the Laplace transform of this. What will be the Laplace transform? Alpha times, what will be the Laplace transform of this signal? Alpha times beta, and then 1 upon s plus 4. Correct? Similarly, for s of minus 3, you just have to replace this with minus s plus 4. So here you will be left with alpha times beta s plus 4 minus beta s minus 4. Correct? So now you're left with what? So this is what? So you have s square minus 16. Correct? This is what you have to compare, and then you have to compare with s square minus 16, and then you have to calculate the value of beta, I guess, right? This is what has been asked here. Let me check it. Yeah, calculate the value of the beta. Right, this is what has been asked. So we are going correct. Then you have alpha beta times s minus alpha beta times 4. Then you have, what is this, beta s, and then 4 times beta. You have to equate it with 16 upon s square minus 16, I guess, right? So this got cancelled. You are left with this all things. So this will be 16 equals to s times alpha beta minus beta minus 4 beta plus 4 alpha beta. You already know that there is no s term, so this will be 0. So alpha beta equals to beta. So if beta is not equals to 0, you will be getting alpha equals to 1. Correct?
Yes, sir.
Yeah, and then this value is what? Minus 16, right? This is minus 16. So this is 4 beta plus 4 alpha beta equals to minus 16. You have alpha equals to 1. So this is 1. So 8 beta equals to minus 16. So beta equals to minus 2. Okay, clear? Everyone? I hope this is clear. Yeah. So not that difficult. You have been given a st already, right? So you have been given xt. Xt was given as some combination of xt itself, alpha times this, and then you have been given the bilateral Laplace transform, right? Even though bilateral was not written, you have to just think that this is a Laplace transform from minus infinite to infinite. You have to integrate it, right? We have, what you have done. You have just calculated for st. You have already know the Laplace transform. For xt also you have calculated the Laplace transform, right? You already know that for if you are replacing with minus t, you just have to replace s with minus s. This is what we have done, and then we have done the calculation. In the end, what we have came to know that this was the numerator part. The numerator part was called cancel. There is no s part, right? So this got cancel. This, there is no s here, right? So that means what, this whole signal, this whole value will be 0. So alpha beta equals to beta. If beta is not equals to 0, any value you will take apart from 0, you'll be getting alpha equals to 1, right? Similarly, you'll put the alpha equals to here 1 here, you'll get the value of beta. Is this clear to everyone?
Yes, sir.
Okay. So the remaining question, the 5 6 problem more that we have, maybe we'll be solving on the Saturday. Okay. And you just come up with all your doubts also, right, everyone? Whatever the doubt that you have after solving graded practice, okay, we'll deal with that. And then Saturday we'll just solve some problem from the Laplace. Next, all three session we'll just be revising the whole concept from week 1 to 12. Okay, and just we'll solving all those portion. Those are most important portion for your quiz paper. The final quiz is the most difficult question that I have seen from like quiz 1 and quiz 2. So you'll have to put in some effort, right? So and we will be solving with you guys all the type of problem that are there in the final paper also. Okay, so we'll try to wrap up all the things till week 12 by Saturday. It's already been done. We'll just be solving some problem, and after that, the whole next week we'll just be solving problems itself that will help you in for the whole final quiz. Okay, and this PDF has already been. Yeah, so you can come up with the doubt session. Yeah, Saturday session you can come up with the doubt session. I'll also solve some problem. You can just give me some problems. We'll try to solve it in the session itself. Okay. So at least you go through the all the content. Yeah. Okay. Okay. So I hope this is done. This PDF also is already there. If you want to go through, just please go through the whole content itself once again.
Okay, sir. Thank
Okay
you.
then. Thanks everyone for coming up, and thank you. Bye. Good night. Bye bye.